Hello and welcome back to Complex Analysis. And of course, as you already know, first I want to thank everyone who supports this channel on Steady via PayPal or by other means. Now, in today's part 18, we will continue talking about the complex integration. In particular, we will define the complex contour integral. For this, please recall that in the last video we have already looked at such curves in the complex plane. And now comes a function f, a complex function f, that maps this complex plane to the complex plane again. Therefore, the definition of an integral along this curve here should represent that we add up the values of the function f at the curve. However, since this is hard to visualize, I would say that we first start with a function that has only values in the real number line. This has the advantage that we can draw the graph of the function f. This means we have a three-dimensional picture. On the bottom we have the plane, the complex plane, and also our curve. And in addition, on the z-axis we find the real values of the function f. Therefore, you could visualize the graph of the function as a two-dimensional surface in the space. More precisely, for each point on this curve here, we find a corresponding value on the surface. In other words, on this graph you find the image of the curve under f. Okay, now you might already see the idea. This whole thing here can be transformed into an ordinary integral. So this one-dimensional curve in the plane we could transform to a straight line, so we have a new x-axis. And the curve on the graph could be our new one-dimensional graph. And then we just have an ordinary integral where we calculate the area. That is just the rough idea how we can define an integral along a curve. Of course, now we have to do this in a very precise way. Hence, now we fix the definition of the complex integral of the function f along the curve gamma. Indeed, more precisely, we will speak of parametrized curves. Simply because the curve in the plane is given by an explicit parametrization. Which means we have a function gamma that maps the real interval AB into the complex plane. Moreover, here we will assume that the function gamma is continuously differentiable. Which is not hard to understand. You can just say that the real and the imaginary part of gamma are continuously differentiable functions. Now, the visualization is the same as above, so we have a starting point gamma of A and an endpoint gamma of B. Hence, when you go with your variable through the interval, you go through the curve here in the plane. However, now we also have a derivative gamma prime. It has also the domain AB and it maps into the complex plane as well. Now, the interpretation here is that gamma prime explains how fast we go through the curve. This comes out because gamma prime gives us the slope for the real and the imaginary part of gamma. Therefore, you can represent gamma prime as an arrow on the path. It gives us the rate of change of the function in two directions. Now, this is important because we really have to factor the velocity of the function gamma in when we look at this picture here. It comes in because in our transformation here, we want to have the start point A and the end point B here. So this would be the best thing when we have the original interval there. However, in this case it's important that we know how fast we go through the curve when we go through the interval. And indeed, because of this connection, you always find the derivative of the curve inside the definition of the integral. And now we finally define this. This is the integral of the function f along the given curve gamma. So please note, this is the new symbol we now have introduced. And now what we do is that we use the integral from a to b of the function f of gamma of t. In other words, these are the values on the curve. However, now we also have to stretch these values by the derivative of gamma. Okay, there we have it. This is the definition of the contour integral. And as you can see, this definition also works for complex valued functions. Simply because the complex version of the integral on the right hand side we have already defined in the last video. Hence the function f can be complex valued. And here please note, the domain does not have to be the whole complex plane. We can choose any domain U as long as the curve gamma lies inside U. In other words, the range of gamma needs to lie in U. Of course, another restriction we need here is that this integral exists. And you already know we have this when the integrand here is continuous. For this reason, let's add the assumption here that the function f is continuous. Okay, there we have it. Now we see with all these assumptions here, this is well defined and we have a new integral notion. And now in order to see that this is indeed useful, we should look at examples. Now for an example, we always need two ingredients, a curve gamma and a function f. Therefore, maybe let's start with something simple. We take the identity the function f of z is equal to z. And our parameterized curve gamma should give us a quarter circle. One possibility for this is that we take the domain as the interval from 0 to pi half, and then we send t to e to the power it. Now let's call this curve here gamma 1 because we will look at other curves later. Okay, now by the definition, the curve starts at the point 1. And then we go around the circle until we reach the point e to the power I pi half, which is I. Now, then we should be able to calculate the integral of f along this curve. So by definition we know this is the ordinary integral from 0 to pi half. And then here into the function f we put in the curve gamma of t, which is e to the power it. In addition, we see that the derivative of gamma is not hard to calculate. It's simply I times e to the power it. And now because the function f is the identity, we just have to multiply these two terms here. Therefore, let's put I in front of the integral. And then inside we see that we have e to the power 2it. And there we have already learned that we can simply use the antiderivative of this function here. And this one will simply be 1 divided by 2i times e to the power 2it. And then we evaluate this at 0 and pi half. Okay, then you should see we can cancel one I here and then we can put in pi half and 0. Hence what we get is 1/2 times e to the power I pi minus e to the power 0, which is 1. However, e to the power I pi is minus 1. Therefore, we have minus 1 divided by 2, so we get minus 1. Okay, so there you see, minus 1 is the value of this integral. Then, in the next step, I want to calculate the same integral, but now with another curve gamma 2. However, gamma 2 should still describe this quarter circle. So now maybe we choose the interval 0 to 1 and then we send t to e to the power I pi half t. Then you see immediately the start and the end point are still the same and we still run on the circle. However, in contrast to before, we are a little bit faster. But as you already know, this should not change the value of the integral. This was the reason for introducing the derivative inside the integral. This means that the integral looks the same, but now we integrate from 0 to 1. And moreover, before we have looked at the curve gamma 1 and now we look at the curve gamma 2. Now of course we don't change so much. This is still the curve given by e to the power I pi half t and this is the derivative. Now we have I times pi half in front. Okay, then in the next step we multiply these values again. And then we just have to calculate the integral of e to the power I pi t. Now this works almost the same as before. We have the antiderivative and then we evaluate at 0 and 1. And there you might already see it. We can cancel I pi here and then we get the same result as before. In other words, we get -1. Now, as we have discussed it before, this result here is not so surprising. In fact, this is what you can show with the substitution rule, the change of variables formula. However, we don't do this now because I want to show you a third example. We still use the same function, but now we take a different curve in the plane. In fact, this should be the straight line from 1 to I. Hence, the start and the end point are the same as before, but the explicit curve is different. Okay, and now we just have to express this line with a formula. Indeed, this is not so hard, because we start with 1, we know we need 1 minus t, and then we add the endpoint I times t. Now, putting in 0 gives us the start point 1, putting in 1 gives us the endpoint I. So you see, this is how you can construct a line between 2 points. However, now you should see, we cannot use the same calculation as before. Still, the formula for the integral along gamma 3 stays the same. In other words, we have to form the derivative of this function here. And we immediately see this is -1 plus I. Now you see, this is a constant, so we can put this in front of the integral. And then inside the integral we find that we have to put this function into f, but f is very simple, therefore we just have this function again. And we can rewrite this as 1 plus I minus 1 times t. Hence you see, we just need the antiderivative of this linear function. This is not hard at all, so maybe let's do this very quickly. It's simply t plus 1/2 I minus 1 t squared evaluated at 0 and 1. Therefore, only 1 gives a contribution. And so the only thing that remains now is to multiply these complex numbers and then to simplify the result. And now I want to skip the calculation and just tell you the result will be -1. And indeed, you should see, this is the same as we had before. And this should be a little bit more surprising because the curve is different now. However, the start and the end point were the same. Therefore, maybe the integral does not care what the explicit curve is and just needs the end and the start point. Now, I can already tell you, in general, this statement is not correct. Nevertheless, for some functions, indeed it does not matter which path we go. And now, as a little cliffhanger, I can tell you exactly this we will consider in the upcoming videos. However, now as an appendix for this video, I want to give you another visualization for the complex contour integral. Indeed, some people describe this as a weighted curve. Moreover, there you also see that the derivative of the curve is important for the definition. Therefore, again, this here will be our curve gamma in the complex plane. And now we know at each point on the curve we put on a weight given by the value of the function at the point. And then the question is it possible to approximate this in a reasonable way? Indeed, it turns out line segments are easy to calculate with, and therefore we approximate the curve with such lines. Therefore, the only thing we have to do is to choose intermediate points, and we call them gamma of t1, gamma of t2, and so on. Then, in the next step, we can say that such a line segment here is given by the difference of both points. In other words, in general, this is given as gamma of ti plus 1 minus gamma of ti. And now comes in the weight, we multiply this with the value of the function on the line segment. This means we have here the function f at a suitable point. For example, we could choose the start point of the line segment, gamma of ti. The idea here is simply, if the line segment is small enough, f will not change so much. Therefore, this here can be a good enough approximation. Then the only thing that remains is that we sum up all the line segments. Now, we don't go into the details here, but the idea would be that we send n to infinity. Hence you see, the idea here is that we make the partition finer and finer, such that the approximation gets better and better. Therefore, you should see that this construction here is related to the ordinary approximation of a Riemann integral. However, for getting a Riemann integral, the difference of ti plus 1 and ti has to be included. And of course, we can just do this by dividing and multiplying by this term. So you see, we didn't change anything here, but now this expression looks like a normal approximation for a Riemann integral. Therefore, in a rough sense, in the limit process, we will get a Riemann integral. The first part will be f of gamma of t, and on the other hand, the last part here will be dt. And finally, the middle part you see is an approximation of the derivative of gamma. Hence, in summary, you see we get our original definition for the contour integral back. In other words, this here is another way to justify this definition here. So you see, it's very important that you remember this definition here. And with this, I think it's good enough for today. I really hope that I see you in the next video. Have a nice day and bye!